Good afternoon, everyone. We'll just start in a couple of minutes. Let's wait for others to join, and I think then we can start. So I think we should start. It's already 5 minutes past 3. So some students are joining. Let me just admit them first. Okay, I just admitted them. I welcome you all to the live session 4. This is basically a problem solving session for the course CMOS Digital VLSI Design. The course is taught by Professor Sudev Dasgupta from IIT Roorkee. My name is Musab Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. Today, we'll be discussing problems related to some other combinational logics, basically a combinational logic style, and and even in fact next week also we'll concentrate mostly on combinational logic, where most of the problems will be oriented around the logical efforts. And I think from week 6, that is live session 6, we will touch upon the sequential circuits. So today is live session 4. Regarding the guidelines, they will remain same. You need to join with the authentic username. Need not to be a real name, but inappropriate usernames will not be added. Camera and microphone should be turned off. Only when deemed important, you can turn on your microphone and asking your doubts. Ample time will be given to ask your doubts. And question and doubts, typically, I ask people to raise their, if they have any query or question. Once I solve a problem or show a solution, you can ask me your doubt. You can always raise your hand if you want to unmute yourself asking your doubts. Otherwise, you will are always free to use chat box. And this the live session is being recorded, and its recording link is available in the Google Sheet that is already being shared with you. Also, the PPTs and the annotated PDF will be made available there. If the session goes longer, sometimes we'll have mini breaks, but typically we don't go that long. And if you have any questions, if you feel that any question remain unanswered during the session, you can always reach out via email, or you can always ask questions on the comments of a YouTube video. I think we are very well clear with the instructions part. Now let's start with the first question of today's live session. The question states that identify the logic implemented by the below circuit. So we are given this circuit and we need to figure out what type of logic is being implemented by the below circuit. So anyone, if you know the answer, can tell me in the chat box. So which circuit is being implemented? What logic is being implemented by the following circuit? Can anyone tell me in the chat box only, please? Anyone else? Okay. So A B. Anyone else? Well, let's just see. So before we proceed, I want to know what type of logic is this? I mean, what type of logic technology is this? Logic is this circuit? Exactly. This is DCVSL. D stands for differential, C stands for cascode, V stands for voltage, S stands for switch, and L stands for logic. Differential, cascode, voltage, switch, logic. Exactly. It basically combines the advantages of CMOS logic plus pseudo-NMOS logic, right? It is typically used where energy efficiencies are primary primary importance. Now coming back to the logic, it is like this. So you have a supply rail like this, VDD, and then you have your PMOS here and here. This goes like this, and this goes like this, and this is your pull down network 1, and this is your pull down network 2. This is your out, and this is your out complement. This pull down network 1 and pull down network 2 are related to each other. They are basically dual of each other, right? They are dual of each other. As you can see here, A and B is connected in series, and you will have A bar and B bar connected in, sorry, A and B are connected in parallel. You will have A bar and B bar connected in series. Here you have output, here you will have output complement. So let's just take this thing here. So this is simply output. This is equal to, let's just call this thing as F, and F is equal to A plus B complement. So this is your NOR functionality. That means this will be your OR functionality. How? So this is A bar dot B bar whole bar. So it is A bar bar plus B bar bar. So it is A plus B. So your OR and you have NOR. So option B is the correct answer. Understood? So now I have a question. I think on this question, let me just make one change here. This is a, yeah. Now it's fine. XOR gate implemented by y equal to a b bar plus a bar b is to be realized using only two input NAND gates. The minimum number of NAND gates required is, I think everyone will know the answer to this. What is the answer? So the question is, how many number of two input NAND gates, minimum number of two input NAND gates are required to implement a XOR gate? 6 is not even an option. Try. You guys try. I'll just wait for a couple of minutes. So the answer is 4. Minimum number of two input NAND gates you require to implement a XOR functionality is 4. Now let's just check how. So this is your circuit. Let's call this point as output of here as X and this here Y. So this here is, if you check, this is AB bar. That implies my X will be equal to AB bar times A whole bar, and my Y will be equal to AB bar times B whole bar. And if you elaborate it by using De Morgan's law, it will be A bar whole bar plus A. So it is AB plus A. This will similarly be equal to AB plus, yeah, it should be A bar. Yeah, it should be B bar here. So this will be AB plus B bar. Now my F is equal to X dot Y whole bar. So it is AB plus A bar plus AB plus B bar whole bar. Again using De Morgan's law, it will be AB plus A bar whole bar plus AB plus B bar whole bar. So it will then will be equal to, again using De Morgan's law. So if I go here, so it will be A bar whole bar dot AB bar plus AB bar dot B bar whole bar. It is A dot AB bar plus B dot AB whole bar. Again using De Morgan's law, so it will be A bar plus B bar plus B A bar plus B bar. So it is A B bar plus A bar B. That is your XOR. So you need at least 4 two input AND gates, NAND gates to implement a XOR gate. Any doubt? Any question? If not, we can move forward to our next question. Just a second. That is question number. This was two. Yeah. That is question number three of today's live session. So let me just make it a bit bigger. The equivalent logic implemented by the following PTL is. So before we going forward, what does PTL stand for? Correct. So it stands for pass transistor logic. So you need to show, you need to tell me what logic is implemented by the below pass transistor logic circuitry. So can anyone tell me what is this? Solve at your end. I'll wait. I'll wait for a couple of minutes. So what is this logic? Can anyone tell me? Equivalent logic of this? I'll wait for 1 or 2 minutes. Then I can tell you. Has anyone solved it? I think just by looking at the variables, you could have guessed the answer. But obviously, that's not the right way to solve a question, but still. I deliberately removed the options here because if options are present, this was a straightforward answer. Even now, it's a straightforward answer, but I guess I'm not able to recall us that circuitry right now. So let me just make a block and then you guys will tell me what it is. I think this should be sufficient. Now you can tell me what is the equivalent circuitry. Yes. Which one? Multiplexer, but which one? Yes. So 4 is to 1 mux. So 4 is to 1 mux means it has 4 input A, B, C, D. How many select lines will be there for 4 is to 1 mux? Correct. 2. S0, S1. And this here will be my I, Y. Can you write the output expression for Y in terms of Select lines and input. Can anyone write it? So one, if you want to use bar in chat box, you can simply write. Let's say if you want to use S0 bar, you can write it like this. So this was, sorry, this was, yeah. You can use a single quotes that will signify a bar. Y equal to, yeah, A S1 bar S0, B S1 bar S0, C S1 S0 bar D S1. Correct. So your output expression is something like this: A times S1 bar plus B times S1 S0 plus C times S1 S0 bar plus D times S1 S0. Now let's just see how pass transistor logic, this given logic implements the 4:1 mux. So these are my inputs A, B, C, D. They can be anything based on the input combination. So let's just say S0 and S1 is S0 is 0 and S1 is 1. That means 0, 1 output will give me B. S0 is 0. That means this transistor is on. So S0, just a second, someone wants to join the call. Yeah. So S0 is 0. That means this transistor is on because input is high for this NMOS. This is something is wrong. So yeah. Mm, mm, okay. Okay. So S0 is 0. This is on. S1 is 1. S1 is 1. This will be off. Okay. So it selects C. So that means we need to change this one accordingly. So let me just show you exactly what happens. So S0 is 0, S1 is 1. That means this is on and this is on. These two are off, right? Now what happens? This B gets passed up to here and C gets passed to here. Now based on the value of S1, either this will get passed or this will get passed, but S1 is 1, so this is off, this is on, so output will be C, right? So this is also correct, but here according to the circuit our output should be like this, right? D is our LSB. If you check, D is our LSB or not. D is, no, it's correct, it's correct. Maybe functionality, I just wanted to show which one is MSB and which one is LSB. Rest you got the idea. So let me just check. S0 is 0 and this will be on and this will be on and then this will be off. So it is correct. A will be passed. S1 is 1. S1 is 1. This will be on. S0 is 1. This one will be on. Yeah. So it is something like this. Okay. So when S1 is 0 and S1 is 1 and S0 is 0, right? So that means this thing C. Yeah, that's what we did. Correct. Yeah, correct. It is correct. So this is a 4:1 mux. Actually, I got confused between the variables, but it is correct. So it is a 4:1 mux. I hope you got the idea, right? So actually, I got confused between some notations. Otherwise, it's completely right. Now we are coming to this question 4. I think you saw a flavor of it last time. But the question is, first of all, I want you guys to tell me what is the logic functionality performed by circuit A and circuit B? Do it at your end and tell me in the chat box. I'll wait for a couple of minutes and then there is a follow-up question to this. Write your answers. What functionality is performed by A and what is performed by B. So what is the functionality performed by circuit A? I see some of you have written XOR and some of you have written XNOR. Let's check for F in case A. F is equal to, so this is A bar B in series, so it will be A bar B, then it's AB bar in series, right? And both of them are in parallel, so it will be OR. And one thing I am missing here is complement. So this is F is equal to A bar B plus AB bar. I know the complement of this is XOR, but let's evaluate. So it's A bar B whole complement dot AB bar whole complement. So F is equal to A plus B bar dot A bar plus B. F is equal to AB plus A bar B bar. So F is XNOR. This is for circuit A. Now let's do circuit B. F is equal to A bar and B are in series and AB bar. So this is same. Pull down is same. So that means F is equal to A bar B plus AB bar whole bar. So this is A B plus A bar B bar. So this is also XNOR. Now the question is, what is the difference between two? What is the difference between two? As one of the students has rightly said, both of them performs the same functionality. But what is the difference between the two? In PMOS of B, there is no parallel connection. So that means pull-up network is different, right? Pull-up network is different for A and B. Now, another follow-up question to this is, which one of the following is a CMOS logic? Which one of the following is a CMOS logic? Why? Option you most of you have said A, but why? You can just tell the answer in one word. This is right. Basically, pull-up network is dual of pull-down network. That's all. So PN is dual of PDN. You can see this also performs the same functionality, and in fact the static power loss is also zero for this case. But we can't say it is a complementary thing because it the output, what should I say, the pull-up network is not the dual of pull-down network. Next week I have a problem in mind where I'll show some circuits or just a circuit whose pull-up network and pull-down network are somewhat similar, and the functionality is being performed as if it is a static CMOS logic. Maybe I have kept that problem for next week. So you guys just answered it rightly. Basically, pull-up network is not the dual of pull-down network, and both of them perform the same functionality, that is the XNOR functionality. Now I have a question which states that implement the following function and its complement using a differential cascade voltage switch logic, that is DCVSL. Assume input and its complement are available. And then we need to tell what is the static power dissipation of the circuit. So the function that we need to implement is F is equal to A bar AB plus A bar B bar. So that is XNOR circuitry that we saw just now. So in DCVSL, we implement F and F bar simultaneously. So here we have F like this, and it can be written AB plus A bar B bar bar whole bar, that is AB A bar. Basically, complement of XOR is XNOR, then whole bar. So F can be written like this, and F bar can be written like this is XNOR, this is XOR, right? Basically, I have written F is equal to A B bar plus A bar B, and F bar as A B plus A bar B bar. Now I need to make the circuit of this. I have written it in complement form because it will be easy to implement. So how will I draw the circuitry? Let me just use some different color for that. We will have like this. Just a second. I'm just making the circuit. So is this correct? I'm sorry about my drawing. Ignore the upper part. You guys know that it will be connected in cross. Other than that, is this correct? Can you check it? Yeah, it is your A, B. This is your F bar, and this right here is your F. Is this correct? Basically, you can check like this. This is your A, B. This is your A bar B, and they are tied to the same connection here. So it will be AB plus A bar B bar whole bar. That is your F bar. Where is it? F bar here. And this right here will be AB bar plus A bar B whole bar. That is your XNOR. You got it? Is this correct? So for make I'll just say first make the logic circuit. such that do Boolean algebra such that it comes in complementing form. That's the first trick. And then its complement also in a complement form, like I have drawn here. So here I have assumed that I have complemented inputs available, right? So even in this case here, so here you have to implement or and nor. So see how easy it is. It you know how or is implemented, right? Nor is implemented. Nor is simply your this gate, and now you have to implement its complemented form. So it will whatever is in parallel will get in series, and your outputs will also be complemented. See, now they are changed into series and they got complemented. And here you have taken one connection, one output, and here you have taken the its complemented form. So it's simply, if you ask me, this extension of CMOS pull down network. That's all. Once you get the form in a complemented form, basically here the trick is first check for the or NOR gate. So it is F is equal to A plus B bar. Now get its complemented form. So that will be like F is equal to A bar dot B bar whole bar F complement, and this is your nothing but your OR gate. So try to get your complement outputs in complemented forms. In that way, you'll be able to implement them easily. I hope you got what I'm saying. True, and obviously, little bit of practice, little bit of problem solving sessions at your end also will help you in this regard. So check some, refer some books and see some problems, and that will also help you. But to be honest, this is more of a practice problem. If you get the idea, you'll be able to do all the problems. So this question, how I approached it, I was given F. So first of all, I wrote F in complemented form, that is B bar plus A bar B whole bar. Then F bar I wrote A B plus A bar B bar whole bar, and then I implemented the same thing. And and also at the same time I used minimum number of transistors, if you can see. And now the part 2 of this question, what is the static power of dissipation of this circuit? Let me put it this way, what is the static power dissipation of a DC VSL circuitry? I think everyone should know this. If you have seen DC VSL, the answer to this is same for everything, almost all. Yes, because at any given steady state, during steady state, there is no direct connection between the VDD and the ground. As a result, the my what should I say, this static power dissipation is zero. Now I have this question. I would like you guys to solve first at your end, because obviously this requires some, maybe part first you can write in the chat box, but part second just do at your end, and then I'll show the solution. So I'll read the question for you. Consider the circuit in figure Q4. So this is the figure question circuit, and the input waveforms. So input waveforms on these. So you need to give the logic function of x and y in terms of ABC, and also you need to sketch the waveforms of x and y. So consider delay in each state while drawing the waveform. That's secondary, obviously. No. Just draw the waveforms of x and y, and also write the what is this logic functionality in terms of a and b at point x and y. Before you proceed with the question, what type of logic is this? In which category it falls? Dynamic logic, correct. So, for a logic having n inputs, how many gates will be required for a dynamic logic? How many transistors will be required? To implement a n input logic, how many transistors are required? Or maybe I'm just, yeah, n plus 2, correct. Basically, n input NAND gate will require n plus 2 transistors. Yeah. Do the question. You tell me what are the functionalities performed at X and Y, and then I'll give you 3 4 minutes to draw the waveforms also. So someone has written the answer, but I guess complement forgot to put the complement sign. So here x is equal to a b bar, right? And then y is equal to x plus c whole bar. Now we need to draw the waveforms. Let's just draw axis first. Here we will have clock, here I'll have x, and here I'll have y. So clock goes high, goes low, and then x. So where should I start x? At which point? A question to you guys. What is the starting point for x here? This one. I mean to say this one. What is this point? What is the value of x? Yes. Why is it at VDD? Uh, it's a yes, PMOS is on at clock equal to 0. It's a dynamic logic, and you have a particular name for this phase when clock is equal to 0. Yeah, pre-charge phase, correct. So it is in pre-charge phase, so it will be VDD, right? Up to this point, let's just consider a bit of delay. Then it will behave based on the functionality. So it is x is equal to a dot b bar. So it is basically a NAND gate, and so it's basically is it a NAND gate? Yeah, no, it's not a NAND gate. Yeah, it's a NAND gate. Yeah. X is equal to a dot b bar. It will, yeah. So it will turn on because a equal to 1, b equal to 1. My output will be equal to 0, and it will start discharging, right? Now what happens to y? So at what point it is y? What should I draw at t equal to 0? So this is also at VDD because of precharge, right? Now what happens to y? Y starts, y behaves as x plus c whole bar. What happens to y? Y also starts discharging, but only up to a certain point. What is that point? Can anyone tell me? It will start discharging, but only up to a certain point. Before we proceed, let me make this better. Y will also fall, but only up to a certain point. It will only fall up to a point where M3 is on. So as soon as M3, that is point X, goes below VTH, it will stop. So let's just say this is VTH. It will be discharged, then it will be constant, and then in the next cycle it will again recharge. So this point is VTH. Got it? You got the idea? So based on the logic circuitry, this will fall, and as soon as it goes below VTH of M3, Y will stop falling and it will be constant, and then the next pre-charge cycle it will be again charged. This was for the input case where A, B, and C were 1, 1, 0. Now let's move forward to question number 7. It states that implement the function f given below. So we have to implement given below using a NORA logic. So I have a function f is equal to GHK and LPLM plus n whole bar. I need to implement this function f. The high impedance node is at the output of, so this is high impedance node f is at the output of clocked inverter as shown in the figure. So here I have to implement, I have to make a circuitry such that f is equal to GHK dot LM plus n whole complement. So here comes the NORA logic, and its input will go to here, and this right here will perform the function f. So what we will do, we'll just start with the first block. By the way, what is NORA logic? Anyone? What is the other name for NORA logic? Okay, so basically X, right? X is the output. So it will start discharging. It will go down, it will go down, it will go down. And also based on the output of this, my what should I say? Y will also be discharging, but this will turn off as soon as my X goes less than my VTH. So there will be no discharge path, right, for Y. So Y will maintain its level. So it will discharge only up to a particular point because of X keeping falling. So basically what happens, based on my input combination of A and B, X will tend to 0, right? But it will have some delay. It will not go 0 abruptly, right? So it has some delay encountered in it. Because of that, as soon as it will go to a point where my input voltage to M3 is VTH, my M3 will be on and it will provide a discharging path to, what should I say, uh, Y. But as soon as it becomes below VTH, this is off and Y will maintain that part and will again be precharged to VDD. So here what I mean to say is this is discharging of X because of the input conditions, and because of this thing my Y also encounters a delay, sorry, a discharge, but it will only discharge up to this point, and then it will remain constant, and then it will again charge in the next cycle. Got it? Because once X goes below VTH of M3, M3 will be turned off and there will be no discharging path, and Y will maintain its level, and then it has to recharge again. Okay, so before we proceed to this with this question, can anyone tell me what is this NORA logic? What is the other name for this NORA logic, or what is this NORA logic? Have you heard of this NORA logic? You have, but with some other name. Heard of this NP logic? In your lectures, I think you have studied about NP logic, right? Maybe once I show the solution, you'll get an idea. So we have to implement this function f using this NORA logic, and f is taken as the output of a clocked inverter, high impedance node of a clocked inverter. So we will have the first block using NMOS that will implement this thing. So we'll have clock bar, or is it just a second? Oh, yeah. So and then here we'll implement this part G using NMOS H K, and then the clock, then it is ground. Now we will give it as an input to CMOS gate. Clock bar. Now I have to implement this part but using PMOS. So it will be like this: L bar, M bar, and N bar. By the way, now you got an idea? Have you seen this type of circuitry where this is made, first circuit is made up of NMOS only and second of PMOS is only? So here what I have implemented is GHK bar. Now I need to take output. So in this, let me just show like this. Here I need to take output. Where should I take? Where should I take my output? Here I'll take output here, and then it will go input to this. Here it is F bar, here it is F. So this is NP logic. I think you guys might have studied it in your lectures, or this is also called NORA logic, where the first block is implemented using NMOS and then the second network is implemented by the pull up network. So this is PMOS. Towards the end of this lecture, I have one more question. I think that time you'll get a better idea of how to approach this type of problem. Any doubts? Any questions? Can anyone confirm me? Have you studied this? I checked your lecture notes. I think you have studied the NP logic. Anyways, I'll show the next question. So I want you guys to implement this question first, and then I will show the solution. So you have this circuit shown in figure below here, and you have to assume inverter switches at VDD by 2, the ideal case, right? So first of all, you need to tell me what is the logic function performed by the following circuit. So what is the logic function performed by the following circuit? And then you have to tell me, explain why the circuit has non-zero power dissipation. So why is there a non-zero power dissipation? And then using a single transistor, you have to fix that such that there will be static power dissipation, no static power dissipation. So the question has three parts. Part first is you have to tell me what is the logic implemented. Second is why is there a power dissipation in the circuit, and third is you have to fix this power dissipation part by adding just one transistor. So let's go step by step. So can you tell me what is the functionality of the circuit? What is F equal to? If you want to answer, you can use chat box, or if you have some doubt, please unmute yourself and ask. If you want to answer, use chat box. Otherwise, you can unmute yourself. Yeah, A B whole bar. Yeah, I'll take that. A B whole bar. Now, I think most of you will know it is A B bar. I mean to say NAND gate. Now the question is, why is there a non-zero power dissipation in the circuitry? Can anyone tell me why does it have a non-zero power dissipation? Please unmute your mute yourself. If someone has turned on the microphone, please mute yourself. So everybody got the question. So my question is, first of all, what was the logic functionality? I guess everybody knows how it's a NAND gate, right? Now the question is, why is there a power dissipation? Can anyone tell me? If you are unable to write in the chat box, you can raise your hand. If you know the answer, please raise the hand. Uh, there's no harm in trying. Whatever you feel like is the answer, please let me know. If you know the answer why there is a power dissipation, please unmute yourself and answer. Yeah, because of inverter, but what's the explanation behind that? If you want, you can unmute yourself, or if you are comfortable in chat box, you can write it there. It is a CMOS inverter. CMOS inverter usually don't have static power dissipation, but why here it will have? So now let me just show the solution. So F is equal to X complement, right? And X is your AB. How? You check it. So it will be 1 only when A equal to 1, B equal to 1, and rail to rail string is provided by this part. So this is F is equal to AB whole bar. Now why it has a non-zero power dissipation? Because of this thing, this NMOS. So NMOS passes weak, NMOS passes NMOS passes weak what? 0 or 1? Exactly. NMOS passes weak 1. So when A is equal to 1, that is VDD, NMOS passes weak one. That means M2 will not turn off fully, and this causes static power dissipation. Now the question is, you have to add one transistor. So where will you add the one transistor, and which transistor, such that the static dissipation power will go? Anyone? No, no issues in trying. Try. So which transistor should I add, and where should I add, such that my power dissipation will be zero, static power dissipation? Anyone has any idea? You can raise your hand and answer. No idea. So what we will do, we'll add a transistor like this. We'll add a PMOS here. Just make it better. What it does, it pulls this node to VDD whenever my x equal to 1 and my inverter turns off completely. But one thing. So this I'll call MR. This MR should be sized such that it should not be strong enough that when A is equal to 0, X will not go to 0. It should be sized such that it will go to VDD by 2 and my X will be going to 0. So by just reducing the power dissipation, I should not hinder my functionality of my circuit. So what I need to do is I need to size this accordingly such that input to the inverter is VDD by 2 when ensuring that X is equal to 0, X goes to low. So we have to size it such that this point also goes to low. Now the last question of today's live session. So I want you guys to do it first. So we have a question. Suppose we wish to implement the two logic functions given by f is equal to w plus x plus y and g is equal to w plus x plus y plus z. Implement these functions using dynamic CMOS cascaded stages so as to minimize the transistor count, and also you have to implement using NP CMOS logic showing circuit level implementation. Assume both signal and its complement are available. So do it at your end. I won't be asking you at any answers because it's the design part. So do it at your end. I'll just wait for 3-4 minutes and then I'll show the solution. And one thing I'll tell you, this digital course or digital design course, it can have, in terms of subjective questions, it can have multiple answers. So I've checked question papers last time. So around 5-6 solutions were there for a simple problem. So there can be multiple solutions to a problem. Unless some constraints are there within which you have to work, then maybe you can limit those solutions. Otherwise, there are multiple solutions to a problem. So try it. And the solution I'll show you doesn't mean that will be the only solution. There can exist multiple solutions, but sometimes you have to evaluate other conditions, other constraints, and we have to put forward our solution accordingly. Now let me just show the solution. We'll first do the dynamic CMOS cascaded stage. So we'll have what we'll have here is first the clock part and then the functionality. So first we will implement. So let me just show you. F is equal to W plus X plus Y, and G is equal to W plus X plus Y plus Z. So G can be written as F plus Z because this thing is equal to F. In this way we can minimize the transistor count. So here I will implement, this will be W, this will be X, this will be Y, this will be F bar, and this I'll give to inverter, which will give me F. Inverter is basically your CMOS inverter. Now F has been implemented. Now I need to implement W. This G. This will go to my transistor, and here I will have other transistor which is W, and this here is, since it's a dynamic, it will have a clock. This right here is F plus W whole bar. This needs to go to inverter, and this will be G. Right. Now implement this thing using NP logic style. That is your NORA logic. NP domino logic, or and NORA for NORA. NO stands for NORA stands for no race. Now we need to implement it using NORA logic style. So we'll have this thing first. This will be clock, same as we did earlier. W plus X, 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 Y, and Z. This right here will go to clock. Now this thing is F bar, right? Take output from here, it will be F, but I need F bar in the next stage only because that is composed of PMOS as we did in the earlier question. So this here will be, and this right here will be W bar. This here will be clock bar. This here will be clock bar, and this will be VDD, VDD, and this here will be F plus W because this thing is F bar, and if it's PMOS, so it will be F bar dot W bar whole bar, so it is F plus W, and in this way we are able to implement the given logic. Got it? Any doubts? So if you have any doubt in any question of today's live session, please let me know. Otherwise, we can close the session. In week 2, question 5. Okay, just wait a second. Let's wait for question, doubt in question, what should I say, this week's question, and then we will take that. If anyone has doubt in this week's live session, this week 4 problem solving session, any question, please let me know. Otherwise, I'll take Pulkit's question pertaining to week 2. So if you have no doubts, no questions, you are free to leave the session. If you want to remain in the session and see what is the doubt, you are most welcome. And I'll close the recording now.